Assalamualaikum, my YouTube students. So, welcome to my channel all about chemistry. So, I am your teacher, Miss Sana. Hope you all are fine. So, this tutorial is about Rutherford's atomic model, number two, Bohr's atomic model, and isotopes and their uses. So, watch this complete video to solve your queries regarding these topics. So, let's get started.
Quote of the day. Do not tell your plans to the people. Surprise them with the results. Students' objectives of today's class are: at the end of this tutorial, students will be able to understand Rutherford's atomic model, Bohr's atomic model, isotopes and its uses. Okay students, so this is your book page number 31. Open this page in front of you for better understanding the concept. Our first topic is Rutherford's atomic model. Students, as you all know that Rutherford performed an experiment in order to know the arrangement of electrons and protons in an atom in 1911. This picture will explain you nicely Rutherford's experiment. Students, you can see that Rutherford bombarded a very thin gold foil about 0.0004 centimeter thickness with a beam of alpha particles. Students, Rutherford used alpha particles which is obtained from disintegration of polonium. Alpha particles are helium nuclei and that are doubly positive charged particles. He noticed that most of these alpha particles passed straight through the foil. Only few particles were slightly deflected, but only 1 in 1 million was deflected through an angle greater than 90 from their straight paths. Rutherford performed a series of experiments using a thin foil of other elements. He observed similar results from these experiments. Conclusions of Rutherford's atomic model. Students, majority of the alpha particles passed through the foil undeflected. This means atoms are mostly empty spaces. Number 2, repulsion shows that positive charge of the atom is not spread throughout the atom. Last one, massive alpha particles are not deflected by electrons. Defects in Rutherford's atomic model. Rutherford's model failed to explain line spectrum. Students, you all know that orbit of the revolving electrons becomes smaller and smaller until it would fall into the nucleus. This would collapse the atomic structure. But in this model, the negatively charged electrons could fall into the nucleus. This does not happen actually. This is your book page number 32. Open this page in front of you for better understanding the topic Bohr's atomic model. Bohr's atomic model. In 1913, Niels Bohr proposed a model for an atom that was consistent with the Rutherford's model. The main postulates of Bohr's atomic model are as follows. The electrons revolves around the nucleus. in one of the circular path, and each orbit has a fixed energy. So, each orbit is called energy level. Number 2, the energy of the electrons proportional to its distance from the nucleus. Means the further the electron is from the nucleus, the more energy it has. Point number 3, the electron revolves only in those orbits for which the angular momentum of the electron is an integral multiple of h upon 2 pi, where h is Planck's constant and its value is 6.626 into exponent minus 34. Next point, light is absorbed when an electron jumps to a higher energy orbit and emitted when an electron falls into lower energy orbit. Electron present in a particular orbit does not radiate energy. And last point is the energy of the light emitted is exactly equal to the difference between the energies of the orbits. Now, our next topic is isotopes. Isotopes are atoms of an element whose nuclei have the same atomic number but different mass number. Once again, isotopes are the atoms of an element whose nuclei have same atomic number but different mass number. Why? This is because atoms of an element can differ in the number of neutrons. Let's take an example. Isotopes of carbon. Carbon has 3 isotopes: carbon 12, carbon 13 and carbon 14. Students, as you can see in this picture, these are electrons present around the nucleus, and nucleus contains neutrons and protons, and there are 6 neutrons and 6 protons. As you all know, students, that number of electrons is exactly same as the number of proton. So there are 6 number of electrons present in carbon 12. Same in carbon 13, there are 7 neutrons and 6 protons and 6 electrons. And in carbon 14, there are 8 number of neutrons, 6 number of protons and 6 number of electrons. Students, you can see these are the isotopes of carbon, and they only differ in number of neutrons: 6 neutrons, 7 neutrons and 8 neutrons. Nuclei and relative abundance of carbon isotopes. In nature, carbon 12 is present 98.9%, carbon 13 is present 1.1%, and carbon 14 is very rare and it is present in nature 0.0001%. Now students, come to the topic uses of isotopes. As you all know, stable and radioactive isotopes have many applications in science and medicines. Some of these are as follow. Radioactive iodine 131 is used as a tracer in diagnosing thyroid problem. Sodium 24 is used to trace the flow of blood. Iodine 129 23 is used to image the brain. Cobalt 60 is commonly used to irradiate cancer cells. Now students, I will show a video to elaborate your concept.
Not all atoms of an element are exactly the same. For instance, here's an example of a carbon atom in its most common form. Notice that it has 6 protons and 6 neutrons in its nucleus. The fact that it has 6 protons is what makes it an atom of carbon. However, the number of neutrons can vary between individual carbon atoms. These variations are called isotopes. Isotopes are atoms of the same element that differ only in the number of neutrons present in the nucleus. Here's one example of a carbon isotope, carbon-13. Notice that while the number of protons in carbon-13 remains at 6, the number of neutrons has increased from 6 to 7. This gives the carbon atom a slightly higher atomic mass than carbon-12, but chemically, carbon-13 still behaves in the same manner as carbon-12. Another carbon isotope is carbon-14. Carbon-14 has the characteristic 6 protons found in all carbon atoms, but in this case it has 8 neutrons. In some cases, isotopes may be unstable or radioactive. Radioactive atoms emit energy or subatomic particles in order to return to a stable state. This is the case with carbon-14. Radioactive carbon-14 has a number of applications in science. Since carbon is found in all living organisms and the decay rate is well documented, we can use carbon-14 as a way of dating how old a sample of tissue may be by comparing ratios of carbon-12 and carbon-14. Carbon-14 dating is commonly used in forensic studies and in studying archaeological remains.
I hope students you all have understood the concept very clearly. Now here I have a very quick recap for you. Rutherford proposed a planetary model for an atom. According to Bohr's atomic model, the electrons in an atom revolves around the nucleus in fixed circular orbits. Isotopes are atoms of an element that differ in the number of neutrons. Radioactive isotopes have many applications in science and medicines, such as killing cancer cell, diagnosing thyroid problem, to image the brain, etc. Now here I have an assignment for you. Question number 1. Describe the contribution of Rutherford made to the development of the atomic theory. Question number 2. Explain how Bohr's atomic theory differed from Rutherford's atomic theory. And question number 3. Define isotopes and its uses.
Hope you all have understood the concepts very clearly. So assignments are given to you. Solve this assignment. This assignment will help you to elaborate your concept. So it's all about from my side. So if this video is helpful, so don't forget to like, share and subscribe my channel. Thank you.